All right, friends, the second comparison test is the limit comparison test. This one has got a little algebra involved in it. The requirement is that both functions we're going to talk about have to be positive. And again, like the other, you're going to pick a function that you already know is either divergent or convergent, one of those two things. So we have two functions, a sub n and b sub n. I always pick the function you're asking the question about to be in the numerator. It doesn't matter, but that's how I do it. And so then b sub n would be the test function. And here's where this gets tricky. There are three possible outcomes. This is, please pay attention to this and write this down on your notes. This is very careful. This is very tricky. You got to be very careful about this. So case one is that when I plug these into this fraction, so the limit as n goes to infinity of the one I'm questioning divided by the test function, when I do this, if it heads to some number L that is not a zero, so some actual number, not infinity, not a zero, then both functions either converge or diverge. So depending upon what you have picked here. What that means is that for this test, you actually can run this several times before you get an answer. So for example, let's say that I have my a sub n here, and I pick b sub n as a converging function, right? And then the test doesn't work. But then you turn around and then I pick, well, let me test my b as a diverging function, and all of a sudden it works, right? That it converges. So you might want to run these several times if you're deciding to use this one. That's the first case. This is the most desirable because it answers very clearly. The less desirable outcomes are this, and this is where it gets super tricky, my friends. For the second case, when you do this, if you get a zero and b sub n converges, then a sub n converges. If you get a zero and b sub n diverges, it tells you nothing. That's super tricky. This is going to be quicksand for many of you, my friends. That if you get a zero, the only answer that's positive is a convergent answer. If you get a divergent answer, you need to either do a different test or test another b sub n. All right. The reverse is going to happen on test 3. That when I do my a sub n over b sub n and I get an infinity and b sub n diverges, then a sub n diverges. Again, this only tests for divergence. So these two are super tricky, my friends. So my advice when I use the limit comparison test is if you don't get a number here, I would just retest. Unless you're really, really sure that you can follow these directions here. You know what I'm saying? So if you know for sure that b of n converges and I got a zero, then you're okay with this answer. But if e sub n is divergent, I would just test something else. Try again. All right. And we'll look at some examples of that here in just a moment. So first, let's look at our very first example here. So we've got 1 over the square root of n plus 1. So again, just like the other comparison test, let's pick a series that you know diverges or converges. This one is really similar to 1 over the square root of n, which you know diverges. Then we can put it in this ratio. So here's my testing curve, the one up here that I want to ask the question about. So that's my a sub n divided by this one here. Okay, the one I know. So I have complex fraction. Remember, I'm going to flip that over. Turns into this. The ones cancel, and I have this. Right? You following the algebra here? Yes. I got this right here. Then what's the limit as this thing goes out to infinity, right? What's my limit here, right? And I put the sum here. I really should have put the limit there. Sorry, friends. Well, that heads to a number, and if it heads to a number, you are happy, right? Because that's when this test is easy. So it heads to a number. You already said that this diverges, so then that one diverges too. Okay? And notice that we really couldn't use this in the comparison test, the direct comparison test, because this one is smaller than that. And because that one diverges, just because this is smaller than that, I don't know that it diverges, right? If that was n minus 1, maybe then we could make that argument and do a direct comparison, but we can't do that with this one. All right, let's look at another. Here we go. 2 to the n plus 1 over 3 to the n. Let's compare 2 to the n over 3 to the n. We know that that converges. That's just a simple geometric series with our less than 1 value here for r. So that means that we know it converges. So we'll plug into our scheme here. We'll flip these. Those cancel. And remember, 2 to the n plus 1 is 2 to the n times 2, right? But you know what's going to happen there, that as these go out to infinity, that the answer is just going to be 1, right? Heads to a number, both converge. Is that going to be 1? No, that should be 2. Doesn't matter if it's 1 or 2, it heads to a number is the point, right? That the ratio is 2, because that's times 2, not plus 1. And so, again, both converge. All right, let's look at... here we get the tricky ones. We start getting our ln's in there. And so again, remember, friends, that the ln of n is always less than n. So if you want to compare, you can compare this to an n, right? So ln of n over n squared, let's compare it to n over n squared, right? And that really is 1 over n. You know that this diverges. So we're going to plug in, and I get ln of n over n squared. Those cancel, ln of n. And notice when I go to infinity, I get infinity over infinity, which L'Hopital to the rescue, right? Because we're doing limits to infinity. And I can take the derivative of the numerator, which is 1 over n, derivative of the denominator, which is just 1. So that becomes 1 over n, and that is 0. Ugh. Now, hang on. This is 0. What does that mean? Let's go back to our list here so we can see. So we got a 0. We got a 0 answer, which is case 2. And we said that 1 over n diverges. The b sub n, doesn't work. This one doesn't work. So then, and I'm not going to do this. You can do this. That'd be good practice for you. So you want to test again. So we test a divergent version of this. Didn't work. So why don't we test something that is convergent? So instead of 1 over n, why don't we test n squared? And if you plug that in, you'll see that that doesn't work either, because that's going to generate a case 3, right? And we can keep going. And so if you try n to the 3 halves, I'd like you to try that. That one does work, and you get an answer out of that. Okay, so some of these you have to do multiple times. So I'll let you practice the n squared, try the n squared, try the n to the 3 halves and see what happens on those. I'll let you do that. Let's look at our checkpoint for this, my friends, here. Checkpoint 5.17. Where's I lost my pen. I'll have to use a blue one. Here we go. All right, so we have the series of 5 to the n over 3 to the n plus 2. Well, what do you want to compare that to? I'd say we compare it to 5 to the n over 3 to the n. Well, isn't that just 5/3 to the n, right? That's a geometric series. We have our r's greater than 1, so we know that this diverges. We know that, okay? So then let's plug in. So I'm going to get the limit as n goes to infinity of 5 to the n over 3 to the n plus 2 all over 5. I'm going to break this apart again so we can see it easily, like that. I'm going to flip these. So this turns into 5 to the n over 3 to the n plus 2 times 3 to the n over 5 to the n. You see those cancel, right? And so that I have the limit as n goes to infinity of 3 to the n over 3 to the n plus 2. And then I think you can see that as n gets incredibly large, this whole thing is just going to go to 1, right? And so then, since it's a number, big giant thumbs up. We love it when it's a number because that diverges, then this one diverges as well.